do you see that you would write the iron and the iron plus 3 and the dichromate to the chromium? Does that make sense? Okay. The second thing you would do, this one's a little more complicated than the first one we did with the copper and the zinc, is balance the atoms besides the oxygen and the hydrogen. So in the first one, we just need to balance the iron, and it's balanced. The second one, what do we need to balance? We need to balance the chromium. So do you see that means I need to add a 2 right there? Okay. The third step is to balance the O using water. Balance the O using water. Tell me if I need to flip back to that slide, okay? Do y'all see that means I need to put 7 waters over here because I need 7 O's on the product side? So I'm going to need 7 waters. Okay? Fourth step, balance the hydrogens using hydrogen ions. Balance the hydrogens with hydrogen ions. Where do I need to put the hydrogen ions? And how many of them? Do you see I need 14 of them on the left side to balance the hydrogens? The fifth step is to balance the charges using electrons. Okay, we did this earlier with the copper and the zinc one that we were looking at. How would you balance the iron one using electrons? Yes. Do y'all see you need to add 1 electron to the product side of the iron one so it balances the charges? Now, let's look at the second one. 14 hydrogens, that's a plus 14. The dichromate has a minus 2. So do you guys see that on the reactant side, your sum total of your charge is plus 12? Do y'all see that? It's plus 12. Okay, what's the sum total over here? You've got 2 chromiums, 2 chromium 3s, that's plus 6. Water doesn't have a charge, so the sum total of the product side is plus 6. So if the reactant side is plus 12, the product side is plus 6, how am I going to balance out those charges? Yes, we're going to add 6 electrons on the left. Okay? Now, once you balance the charges using the electrons, you have to make the electrons equal. You can't have iron oxidizing to produce 1 electron, but that dichromate reducing and requiring 6. So if you've got 1 electron at the top and 6 electrons at the bottom, what you have to do is multiply this top equation by 6, because that's going to make the electrons equal. So if you multiply the top equation by 6, that would be 6 iron 2s, 6 iron 3s, and 6 electrons. Okay? To show you what I'm doing, y'all, what if the iron equation had produced 2 electrons and the chromium equation had required 3? Do you see that our common multiple of 2 and 3 would be 6? So we would have to multiply the top one by 3 and the bottom one by 2. You follow? If it had been 1 electron and 2 electrons, we would have multiplied the 1 by 2. Okay? So then we can sum up the total overall equation here. The 6 electrons are going to cancel out, and the sum total of the equation is 14 hydrogen ions plus the dichromate plus 6 irons, iron 2s, yields 2 chromium 3 ions plus 7 waters plus 6 iron 3s. And that is the whole reaction balanced using the half reaction method. Okay? So, going back to what we did, the first equation we balanced today, the copper and the zinc. When you guys did this in lab in Chem 1, you had a beaker like this, and you took a piece of zinc, you put it in the beaker, and as you said, it turned clear. Because what happened is the zinc, this is zinc solid, oxidation number is 0. All this zinc started losing 2 electrons. It started giving it to the copper 2 that's in here. When these copper 2s gained the 2 electrons from the zinc, it precipitated out as solid copper. And since this was getting oxidized, y'all didn't use a bar like this, but you use granular zinc. Oxidized means this bar is going to get eaten away. Do you see that? As it oxidizes, it turns into zinc plus 2. And so this bar is going to get a lot smaller.
Can you do it?
Huh? Can I do it? Yes. I don't want to do it in that because I got something else I want to do with that. Okay? What I want to do with that is the gist of the chapter, electrochemistry. It was discovered that if you take these 2 reactions, the copper reduction reaction and the zinc half reaction, and you separate them, you can build a galvanic cell or a battery. And there's a picture of one in your book. Okay? So, what you have on the right side, obviously, y'all, there's a copper sulfate solution, right? That piece of metal is solid copper, okay? On the left side, you have a zinc sulfate solution, and that piece of metal is solid zinc. Now, we know, based on what we just wrote, that zinc will be oxidized and copper will be reduced. How do you know what's going to be oxidized and what's going to be reduced? It depends on something called its reduction potential. In your book, I'm saying this because I'm recording it for Sam. In your book, table 19.1 is a table of standard reduction potentials. And they're listed in order of their ease of oxidations, okay? And so we'll look more at this table in a minute, but I want you to look at the galvanic cell here. instead of having the copper sulfate solution and putting the zinc electrode in the copper, you would just have electrons being transferred right here. But if you separate them out, you can actually, you see the little black alligator clip and the red alligator clip, you can make the electrons still transfer, but they go through here. And electrons moving creates a voltage, creates electricity, okay? And so you can make the electrons move externally. This little tube here is called a salt bridge. Okay? And what you're going to have on your salt bridge is a salt. And it has to be a salt that won't react with whatever you have here. Like it can't react with the zinc sulfate. It can't react with the copper sulfate. So a lot of times it's like sodium chloride, group 1 metals, because they don't precipitate. You could use nitrates because nitrates don't precipitate. So like potassium chloride, rubidium nitrate, sodium nitrate, lithium chloride, whatever. You put in your salt bridge. And so what's going to start happening, y'all, is this zinc electrode is going to be oxidized, and you're going to have a lot of zinc 2 ions going into that solution because the zinc is going to be giving up electrons. The electrons are going to flow this direction because these copper 2 ions that are in solution are going to turn into solid copper. What is it? Did he just get a bad grade?
My ex-girlfriend's pregnant.
Hang on, I'm recording. Sam, you're going to miss this. Okay, we're back on recording now, so we're going to do chemistry. So, we know the zinc is going to be oxidized and lose electrons. They're going to flow to the copper. The copper is going to get reduced. So what's going to happen over the course of this reaction is this zinc electrode, it's going to lose mass because it's getting oxidized. The copper electrode is going to increase mass because, see, the copper is getting reduced. The purpose of the salt bridge, y'all, if you didn't have it, then what happens is this cell where the zinc is, it's called a cell, by the way. You get a buildup of zinc plus 2 because the zinc gets oxidized. The cell where the copper is, you start losing all your plus 2s because it's getting reduced. And what happens is you get a big difference in charge as the zinc side builds its positive charge and the copper side decreases. And so the purpose of the salt bridge is the anions from the salt, the negatives, flow here to try to neutralize this buildup of zinc. And the cations from the salt flow this direction to try to neutralize, to try to replenish the copper cations that are getting reduced. Okay, is this making sense? You have an anode and a cathode. Reduction, copper 2 to copper solid, reduction occurs at the cathode. Zinc solid to zinc plus 2, oxidation occurs at the anode. Okay, and the way I remember that is reduction cathode, they're both consonants, oxidation anode, they're both vowels. So, let's look at your table here of standard reduction potentials. Table 19.1. And I know that I didn't back up enough so that y'all could see it, but I want to point something out because you're looking at that table in your hand. Do y'all see that? I can't draw on it and show it to Sam right now. There's an arrow going up the right-hand side. And labeled on that arrow, it says increasing strength as an oxidizing agent. Okay? Y'all, increasing strength as an oxidizing agent means the stuff at the top is what's going to get reduced. Oxidizing agents are reduced. There's also an arrow pointing down the right side here, pointing down, and it says increasing strength as a reducing agent. The reducing agent is what is going to be oxidized. Okay? It's also important to note that this table is all standard reduction potentials. So that means every reaction on this table is showing things getting reduced. Like look at the first one at the top. F2 plus 2 electrons yields 2 fluoride ions. F2 starts out with a 0 charge. It ends up as a fluoride ion. The charge goes down. It's getting reduced. So when you hook up your cathode and your anode, like if we're looking at this zinc and copper system, find copper on that table. Y'all, did I find the right one? I think I just found cobalt. We're just talking electrochemistry, Tyler. Okay. Here's copper. Okay, I know you can't read what I'm circling, but can y'all see it on your sheet where the copper is?
Yeah.
Really? Okay. Where's the zinc? Okay. Copper's here.
Oh, wait, I found zinc. It's
Okay.
right here. -0.76.
Was that really your mom?
Yeah.
Okay, so since the copper's above and the zinc is on the bottom, that tells you that the copper is going to be reduced. Y'all, it's literally proximity on the table. The top one's going to be reduced. It's going to be the cathode. The bottom one's going to be oxidized. It's going to be the anode. Now, because this is a table of standard reduction potentials, what that means is, okay, copper is going to be reduced. The reaction shown is what happens for copper. Is this the reaction for what's going to happen to zinc? It's the reverse of this that's going to happen. Okay? So, when we look up the right-hand side and it says increasing strength as the oxidizing agent, what's going to be reduced is here. It's on the left side of those equations. When we look at the arrow going down the right side and it says increasing strength as the reducing agent, that means what's on the right side is what's going to get oxidized. Are y'all with me? Kind of, sort of? Okay. We need to calculate how many volts will be produced by this reaction. And how you do that is you calculate what's called a standard cell potential. Remember what that degree symbol means?
Concentration.
It means the concentrations are 1 molar. It means the temperature is 25 degrees Celsius. It means the pressure is 1 atm. Okay, it means all these standard perfect conditions. And how you calculate the cell potential is you take the cell potential at the cathode and you subtract the cell potential at the anode. Another way of stating that is to say that the cell potential is equal to the reduction potential minus the oxidation potential, because reduction is at the cathode and oxidation is at the anode.
You think I'd be a good baby daddy?
I think with some maturity, yeah. You can be. It can make you be mature.
Man, I ain't got time for all that mess right now.
There you go. See? Fair enough. That's not what you had planned right now. How old are you? 19 years old?
20.
Yeah, that's young. Sometimes our plans go awry. We don't get to choose. We did make choices, and
Yeah.
that's it. So, the cathode, the reduction potential, is what's going on with the copper. What number do you guys see there? I circled it in red. What's the copper number? positive 0.34 from your table. So 0.34 volts minus, what's the zinc number from the table? I lost it. Okay, yeah, I see it now. You're right. Negative 0.76 volts. Okay, what you do not do, even though the bottom reaction, the reverse of that is happening. You don't change the number or anything. You take it straight from the table. You don't make the negative positive. You don't flip it around. Okay? So 0.34 minus a negative 0.76 gives us, how many volts should we produce? $1.10? Okay.